Hello, I want to begin by thanking the organizers of the Café con Leche for inviting me to give this talk. I feel honored to be part of the Lathisms community. Um, Today, I want to tell you about optimizing reconstruction of undersampled magnetic resonance imaging for signal detection. By the end of this talk, I hope that you'll know what each of these words mean. Also, I want to say that the way that images are typically chosen in reconstruction is whether the error is small. In our work, we look at more what the image will be used for. For example, detecting a tumor. And that's going to be the fundamental thing that is different about what we do than what most of the other groups do. I'm a professor at Manhattan College. So I want to begin by just having a list of acknowledgements. I can't possibly thank everybody who was involved in this project, starting with the Manhattan College student collaborators, my faculty collaborators at different institutions. You'll see that part of how I think about science is a very team effort. I also have gotten support from Manhattan College, both for my students and for myself in terms of grants and external funding from the National Institutes of Health. In the spirit of sharing my professional trajectory, I want to start by saying a little bit about my family. I'm from Honduras originally. My dad was one of 11 children, and he was the first one to wear shoes before he went to school. My mother was one of two sisters, and my abuelita had a store in Tegucigalpa, the capital city, where she would sell, food, and it was like a convenience store out of her house. Thanks to both of my abuelitas, my grandmothers, who really pushed education for both of them, they both became medical doctors at a public hospital in Honduras. And if you can see in this photo, it's an old photo, but they were smiling and they were doctors together. They met in medical school. A lot of why I do what I do really comes from them. The push for education, the medical application, the connection to developing countries. These are all things that really came, from my parents and my grandmothers. And when we think about family, there's the family that you're born into, and here's a picture of all of us, in our stairwell, and then the family that you choose. And this is my current family, my wife and kids. In this setting, I have been extremely fortunate of having a very supportive family who has inspired me, and really taught me about the need for a community to be for the success of the individual. So maybe the clearest example in my family is that my dad was the son of the kids. So the older kids would basically help pay for his school, even though they hadn't been able to go to college. And each month, they would contribute a small amount of money that would help my dad stay in school. And all of the kids after my dad ended up going to college. It's this idea of all of us being part of a community, a family that helps each other succeed, that came from my own blood family, is something that has helped to shape my view of how we should be in academia. I also have been very fortunate of having the support of advisors. So my undergraduate advisor, Rob Root, and my PhD advisor, Harry Barrett, Rob Root at Lafayette College and Harry Barrett at University of Arizona, were really fundamental in terms of helping me believe that I could achieve, success. And they believed in me, and they helped me at every point along the way with advice that sometimes I followed and sometimes I didn't. But I didn't feel alone. Anytime that I was on a crossroads and I didn't know which direction to take, I knew that there were people who had more experience than me who would help me navigate academia. And in the state, having come to the States from Honduras, I didn't know exactly how everything worked, and these people have been a huge part of why I am successful. In a way, in my own way. So the the mentorship also developed into friendship, which is a added blessing in the relationship. And it's something that even in terms of my own mentoring of students, I try to do as well. Look at my students as people, right? And sometimes students don't look at faculty as people. But these two mentors of mine helped me develop that kind of relationship early on. And throughout my entire career, anything that I have done has, to a significant amount, been because of the mentorship and support I got. And because I've been so fortunate, I felt that it was important that I, give something back to, now that I'm older, to people who had less experience or having come out of Honduras to developing countries. So in this way, we're in a situation where there are a lot of different ways to give back, and one needs to be deliberate as to where we're going to spend our time. We have a very finite amount of time, and spending your time in a way that is both meaningful to you and where you can make an impact, is important. And also that means making difficult choices and saying no to things that are really cool things to do that you would want to do, but just being realistic about the amount of time that we can spend on something. Ideally focusing on the things that you care most about. For me, because I am from Honduras, I felt like supporting mathematics in the developing world was a place where I could make a more unique contribution, a more significant contribution than many other areas that I feel are important as well. So because of that, I was a volunteer in the volunteer lecturer program. And in this program, part of the International Mathematical Union, they send volunteers to different countries around the world to teach courses that are not available in that country. In my case, I taught graduate numerical analysis in Cambodia for a couple of summers. Other mathematicians have went to El Salvador or even Honduras and places in Africa. So there are many places around the world where you can go and volunteer and teach an intensive graduate course. So my course only lasted 3 weeks. We met every day, for 3 hours a day. And so that's 45 contact hours. So that's the roughly equivalent that you would have in a course in the United States. And it was a part of a master's program trying to rebuild the mathematical community in Cambodia after the Khmer Rouge killed everybody who was educated. So it was a place where there was a large need, and there was, again, a sense of community of people helping out. After that experience, I became a member of the Committee for Developing Countries of the IMU, and as part of that committee, I was involved in a program to support the students. So the volunteers would go and teach, and we identified the need of supporting the students as well. So this is the GRADE program. That's the program that I'm currently a part of. And we give small scholarships to students in developing countries so that they don't have to have full-time jobs on top of doing mathematical research. And then, in between those two experiences, I was part of a report of mathematics in Latin America. I want to show here, this is the group of people who worked on the report of mathematics in Latin America. This picture is a meeting of the volunteers for developing countries. And there's a component where we all need to pick how we use our time. But in a way, it's sort of like Lathisms, the people who are volunteering their time for these kinds of projects, they're like a pleasure to work with. So I encourage you to think about very deliberately in the way that you feel that you can, the way that you can spend your time best. Now, so a big part of my mathematical life is mentoring research. So it's mentoring student research, and I came from a applied mathematics, medical imaging community, and then I'm teaching a mathematics department. So I've been learning a lot from both communities as to how to mentor students. One of the places where I felt I learned a lot was Project Next. So if you have the opportunity to be part of this MAA professional development program, I would highly encourage it. The Math Alliance is another place where I've learned a lot about how to mentor students. And also taken advantage of the resources they have available to help me mentor students, especially students who are underrepresented. And SACNAS is a conference that everybody here probably knows, but I feel I learned a lot of how to mentor students, from a trip to SACNAS. So there's lots of things that one would think about how to mentor students. And there's a couple of things that I would say. The first one is, even though we're the mentors, I would say we should spend more time listening to the students. I often think about the student's perspective. I was an undergraduate student once doing research, but that was a long time ago. And the kinds of things that students say that they want is to get to know their faculty. So one of the things that I try to do is to go to have coffee with students, for example, in a regular basis, so that we work on the research, but we also have the space to sort of share something about our experiences. I would also say that I always am, so I might be picky, but when I give feedback, I do it with care. And that just reminds me of my advisors, where they were really tough when I gave them presentations, but I felt that they were tough in the way that they prepared me really well from when I went to an external talk. Whatever questions I got from an external speakers usually were not as tough as the ones I got from my advisor, but I had seen them before in a more safe environment. So provide feedback with care. Then I guess the last thing that I'm going to say, especially for those of you who may not have as much experience in undergraduate research, it's the best time spent is thinking really carefully about the problem before you start involving students, because it's easy to get trapped. So in my world, I try to think about something that's mathematically interesting, accessible to students, and clinically relevant. And I usually think about it in a way that there needs to be simple, specific examples that the students can work on first, and that I'm pretty clear as to how to do. And then that initial, very hands-on beginning that helps them get involved can grow into things that I don't know how to do that are, more challenging. So, but thinking about it in a scaffold way, where you start with something that that they're going to be able to get, some progress at the beginning, and have it be something that can grow into a larger project is one of the ways that I think it's important in terms of creating a problem that is both interesting to you and that helps the students develop the kind of problem-solving skills that are useful in research. So here's some big picture things that I feel that I've learned during my time. The biggest indicator of success that I have seen is persistence, stubbornness. Just sticking to it. The tougher things that you lose, like a PhD or research, teaching. Everything takes a lot of time, and you're not going to be really good at it when you begin. And it's a matter of trying to do a little better each time and stick it to it for a long time. And this growth mindset of when you have a challenge, think about it as an opportunity to learn more. So you're always like learning more. You're always fixing mistakes and thinking about each time this is an opportunity to do things a little better, and just sticking to it. Very recently, early in my career, I was just very focused in trying to get a PhD or, try to get tenure. And now I'm in a place where I really have to think. I have more space to think about how to align my time with my values. There's so many things that we can do. Just being deliberate about, I have a finite amount of time. How do I want to use it? And that includes family, friends, and work. And thinking about not letting other people make priorities for you, but having you be deliberate about how you make those choices is something that I would encourage you to do. I love working with other people. I think it makes the work better and it makes it more fun. And in particular, in my area, in order for me to have clinical impact, I need to work with people who are radiologists, people who are biomedical engineers, people who are electrical engineers, and this is both in terms of making the work better, but also it's more fun. I would encourage you to involve other people in your work. And so wherever I have been, there's always been things that I wish were better, and things that I really liked. And one of the things that I see that I feel it's important is that in anywhere you are, and whenever you talk to anybody, it doesn't matter if they're like at Stanford or they are in other places. There's always things that could be better. There's always things that could be worse. So just valuing the opportunities that you have wherever you are, something that, again, that I try to be more deliberate, and I would encourage you to do the same. Okay, so that was the career path sort of conversation. Let's talk about magnetic resonance imaging. MRI uses a large magnetic field to image the properties of atomic nuclei, mostly hydrogen. There's no negative side effects to MRI that are known, so except for possibly heating in some extreme situations. So this is very different than a CAT scan. In an X-ray CT scan, the X-ray radiation increases the likelihood of a mutation in your cells, like possibility of cancer, but that does not happen with MRIs. So if you have to get repeated MRIs, that's not something to be worried about. But if you had repeated CAT scans, then that's something that you should be worried about. And that's a picture of me going into an MRI scanner, a few years ago. So in the mathematics of that, so it's kind of like a rather beautiful thing. There are a lot of assumptions that need to be made to get to this point. But in the simplest of models, the data that you collect in MRI is the Fourier transform of the underlying object. So if you have a brain, you're basically measuring the magnetic properties of hydrogen, of water in the brain, and you're collecting the Fourier transform of the object. So if you, for the simplest acquisition and ideal conditions, the way that you would create an image, you would start with the MRI data, you would take an inverse Fourier transform, and then that would give you an image of a brain. So for those of you who may not be completely familiar with the Fourier transform, this is the forward Fourier transform. And what you see is f of x, y is a function in image space. And basically, the Fourier transform is a change of basis into the complex exponentials. So you can see that each of these values of the Fourier transform is a projection of the function in the spatial domain into the Fourier domain, or the complex exponentials. And these are frequency dependent. So, basically objects that, low frequencies are, generally describe larger features, and high frequencies, things that wiggle a lot, would represent finer frequencies. Now, where is it that we're going to be doing our particular work? Our particular work is going to be focused on undersampled images. If you collect the entire of the Fourier domain, that takes a long time. So MRI is slow. So there's a huge amount of effort trying to speed up MRI. And one of the ways that you do this is by not collecting all of the Fourier frequencies. And there are different sampling masks that are used. So basically, you only collect some of the data. So in this image to the left, instead of collecting all of the data, only the images in the regions in white are collected. So in this setup, the low frequencies are in the middle. So you collect all of the low frequencies, but then you randomly collect some of the high frequencies. And then you reconstruct the image. And what you see is that if you had the fully sampled image, this is what the brain looks like. But if you are doing this undersampling, what you get is these artifacts. And it looks a little bit like the brain is wrapping around itself. And you can see these vertical artifacts in the horizontal direction of the brain. So what we want to do is we want to basically reduce those artifacts and see how they affect the ability to detect the tumor. Now, the way that we're going to do this is by constrained reconstruction. You might have come across this under the name of compressed sensing. That's a combination of random undersampling and a priori assumptions about the image itself. Now, the two different dimensions that are most commonly used in terms of compressed sensing are total variation, which is basically the L1 norm of the gradient, and the wavelet domain. So these constraints basically are saying This is our data G. So this data agreement term says when you reconstruct the image, match the data, but in addition, make the gradient small, and in addition, make the number of of wavelet coefficients small. So basically, if you are sparse in the gradient, piecewise constant functions, or sparse in the wavelet domain, this gives you additional information that you can use to reconstruct your image. From a probabilistic perspective, these two are priors. Now, when we do that, people have been doing that. They create nice images. We are interested in seeing, does it help in terms of a clinical task? And this leads us to task-based assessment of image quality. In task-based assessment, you basically have to identify the images that you're going to evaluate over, whether you're going to use a human or machine observer, and what is the task? Is it detection of a tumor? Is it sizing of the tumor? That would, a detection would be a detection task. A sizing would be an estimation task. So this is the framework that we're going to use to see the image, one image is better than another. Now, how does this go about doing? From a detection task, this is like hypothesis testing in statistics. So it's going to turn out to be, we're going to use a test statistic to determine whether the signal is present in one image or not. And in this setting, what we have is a test statistic, and here's a distribution under the signal not being present, H naught, and this is the distribution of the test statistic under the signal being present. So typically, we have to pick a threshold, say TC. And now if the value of your test statistic is above TC, then you say the signal is present. The tumor is there. But if there's two things that could happen there. One of them is that this tumor is not there, and that's the false positive fraction in blue. And the other one is the tumor is there, and then you can have the entire area under this green curve to the right of the threshold is the true positive fraction, right? So for every threshold, there is a different true positive fraction and false positive fraction, right? So now what happens if the test statistic is below that threshold? Then you also have the fact that you say, no, there's no tumor there, but the tumor may be there, and that's the false negative fraction. And then all the area under blue below the threshold is the true negative fraction. So you can see how basically for every threshold, there's a different false positive fraction and false negative fraction, true positive fraction. So you could vary the different thresholds. And this is what we're going to do to generate a receiver operating characteristic curve in the next slide. But another key idea to notice is that the more separate these two curves are, the easier it's going to be to detect the tumor. So in a way, what we're doing is we're saying we want to pick the acquisition or the reconstruction that separates the images with the tumor and the images without the tumor better. So let's look at the receiver operating characteristics curve. So what we see is that for every threshold, you have a true positive fraction and a false positive fraction. And if, for example, if you have a threshold that is very far to the left in the previous slide, then basically you're going to have a true positive fraction of 1, right? So you're going to say everything that is a tumor is a tumor, but you're also going to have a very large false positive fraction because everything that doesn't have a tumor is also a tumor. So by picking a different value of the threshold, you get a different point on this curve. The way that we're going to pick, so the higher the curve, it means for each false positive fraction, the true positive fraction is higher. So between these two curves, we would pick the curve that is higher. A way of summarizing that is the area under the ROC curve, which is effectively can be interpreted as the fraction of times that you correctly make a decision. So the area under the ROC curve is how we're going to say we think these images are better than these other images. Now, so this is what happens in a detection task. We're going to model this using a linear model. So the linear model is basically going to take the image, is going to do an inner product with a template, and then it's going to add some internal noise. So in this setting, let's think about what this is. T is the statistic, right? That's what we're using to decide whether the tumor is present or not. G is the image. Template, we're going to talk about how to generate this template in a second. But here's where we connect a little bit with vision science. When a human is trying to make a decision, they don't make the same decision every time with the same pair of images. So that means that there is a level of internal noise, and we model that in here. Now, what we do to generate the channels is, well, we have an image, and then we're going to basically do an inner product with channels. We're going to see different kinds of channels to do this, but you can see how the linear algebra is coming into this problem in a very natural way. And the way that we're going to apply this template, and this is where we get into a little bit of the machine learning or statistics associated with statistical detection theory. And the template that we're going to use is effectively the linear discriminant. Is going to, from an imaging setup, is going to uncorrelate the data and then apply the signal as a template. And to implement that, what we do is we compute the inverse of the covariance matrix in the channel domain. We multiply it by the signal in the channel domain, and then we use that as a template. And there's a bit of derivation as to how this comes about, slightly outside of the scope of the talk. But the thing that I do want to say is that what we're doing here is a very simple classification task in the way that you would learn it in a machine learning class. Except that we're going to be doing it to model human observer humans making this decision. Having said that, the first set of channels that we're going to use are not used to model humans. They're used to model the best possible observer performance, basically a machine observer. And these are Laguerre-Gauss channels. And if we look at these channels, they are basically products of Laguerre polynomials and with Gaussian envelopes. Here we're plotting the first 3 channels, and actually the first right. So here what we're plotting is the first 3 channels, and then A, B, and C. And then you can see the profiles of the first 3 channels. This we're going to be looking at 2 lesions that we're detecting. This E is the small lesion, and G is the large lesion. And here we're looking at a cross section of what the small lesion looks like and what the big lesion looks like, along with the approximations using just 3 basis functions. And actually, I think in this case we use 10 basis functions. So you can see that the lesions themselves are very well approximated using just 10 basis functions. Now, so the work, so this is all that I gave you was a little background about how MRI works and how statistical detection theory is going to be used in this problem. But now we're going to put them together, and we're going to put them together in basically 3 different goals. The first aim is going to, and it's divided into aims because generally grant applications are divided into aims, and in my case there's 3. So the constraint reconstruction using an ideal linear observer. First, we're going to try to see how undersampled reconstructions affect the performance of our best possible observer. So to do that, we're going to look at the large signals and the small signals in a variety of backgrounds. So one of the things that is different about this work is that our backgrounds are coming from a database of brain images. And we have, so things that affect the effect of these wavelet and TV sparsity is the signal to noise ratio, the amount of noise basically in your images. And what we do is we need to generate lots of signals and backgrounds in order for us to do our detection task. And what we are seeing here is basically a grid of small lesions and big lesions used to evaluate the different amounts of regularization. Basically, we're going to see how does the regularization affect our ability to detect these lesions, and how does it affect a large lesion and a small lesion. So let's first look at what images look like when you do TV or no TV. So if you look at the image to the left, both of these have signals, and this is undersampled. And what you see is that there is what you see is that there is these undersampling artifacts that occur in the um, in the image without total variation, and those undersampling artifacts are gone. But so this is undersampled, right? So these are artifacts that are gone, and you go, great, we got rid of the undersampling. But then what you see is that the image that where we use the total variation, it's blocky, so it's blurry, right? So the trade-off is, how does removing the artifacts but adding this blurring affect our ability to detect a tumor? Now, so this is the results from that study. What we did is we changed the regularization parameter for total variation, right? So we kept from, this goes from 10 to the -8 to 10 to the -1, and it's fairly constant for the large signal. Basically, the large signal isn't affected as much by regularization. And when we look at the small signal, and we see it's affected more, but it remains relatively constant until a large amount of regularization where it decreases. So this is a bit surprising, because what we're seeing here is that it seems like compressed sensing doesn't help detection of tumors that much at this SNR levels. So then we look at the typical measures for evaluating image quality, something like ensemble mean square error and structural similarity. Both of these are measures that are typically used. Basically, they look at how close are the images and the reconstructed images. And what we see is that it does seem to appear like there is a large improvement in detection performance if you have a regularization. So what we see here with the mean square error, it says, oh, you should definitely have this amount of mean square error. It's better than if you don't have any. And if you look at SSIM, it does the same thing. It says for this amount of mean square of regularization, doesn't do nearly as well as for this amount. So what we're seeing is that the mean square error tells you should use this level of regularization, but the detection performance is not different, right? So that's the part where we are sort of espousing. It doesn't matter if the mean square error is better if it doesn't allow you to detect the tumor better. And the canonical example for why this is like, you can make the mean square error really bad by just adding salt and pepper noise to an image. But the salt and pepper noise, it doesn't look like the signal itself. So it doesn't affect your ability to see the tumor that much. So let's look at a little bit about subjective assessment, right? So now we look at, so people look at mean square error, they also just look at the images. Here are 3 different levels of regularization. And here you can see the percent correct, the area under the ROC curve, 0.9, 0.92, 0.93, 0.90. These are basically these are the same signal, but 5 times as bright as here. In the lower row, it's just hard to see the signal. We can see that from the first image and the last image, they look very different. The first image looks much noisier than the last image. But if your task is to detect that tumor, the percent correct that you'll do it right is the same, still 90%. So our point is, it's really hard to subjectively decide which image is better than the other. So if pause the video and take a moment to look at those images, and you can decide which one you think is better, and then check to see the percent correct above and see if it matches with what you think. So that was the first part of the work. The second, actually, the first all had to do with machine observers. Second one has to do with human observers. So if you go to, for a medical procedure, the person who's going to look at the images is going to be a radiologist in the end. So we need to model the ability for humans to look at images to detect tumors. So we're going to do experiments. There is a small medical monitor and a computer in my office that we turn off all the lights and then we run experiments. So this is kind of exciting for me as a mathematician to have a small experimental lab, and then we develop the mathematical models to predict the data from the lab. So we both produce the data and run the mathematical models. And what we typically do is a two alternative fourth choice experiment. So what we have is we have the signal in the middle, and then two images of different backgrounds. And the goal is to determine which of the two images has the signal. So you can pause the video now, and then I just want you to guess and see, is the signal in the center of the image to the left, or is the signal in the center of the image to the right? Okay, so in this case, I think it's pretty clear that the image is on the image to the left. I hope that that was clear to you. In a typical experiment, you would do this 200 times, and 4 or 5 different people would do that. And that would allow us to say, this is the fraction of correct times that one would detect the signal for that particular level of regularization, for that particular ensemble of images. So going back to the task assessment of image quality, the ensemble of images are a particular set of MRI scans. The observer would be human, and the task, the detection of that signal. So what we see here is the particular tool. And one of the things that's pretty cool about involving students in this work is that there are parts of this work that are not so accessible, like the generation of the images from the MRI data from a realistic study is pretty difficult, requires a lot of background in medical physics. But the creation, once you have those images, the creation of these observer studies is something that is accessible to students. And the linear models that we use to analyze them is also accessible. So it's beautiful in that it combines a work that is relevant to the medical community, but it is also accessible to undergraduates after their sophomore year. So we do these observer studies, we collect this data, and then we're going to need to model the output of those experimental studies. And here is where we are inspired by the vision literature. And in this case, what I want to show you is the contrast sensitivity diagram. So what we see in the left is a sweep grading. So from left to right, you see the bars get narrower. From bottom to top, they get fainter. And you think that they go away, but they're just getting narrower and fainter. What you can see is mostly the bars in between. In a way, what that's telling you is that if a object is too big, it's actually hard to see. If it's too small, it's hard to see. And there are a scale of objects where it's easier to see. Like you need less contrast to see it. And this is same. So the results of this kind of study are shown here. And what you see is that for some middle frequencies, you don't need a lot of contrast and you can see it. And then for other frequencies, you need a lot of contrast before you can see it. So this sensitivity to middle frequencies is basically the key idea that's going to motivate the kind of models that we're going to have for human detection. So when you saw the Laguerre-Gauss channels, they looked at every frequency. They were not frequency selective in the same way as these sparse difference of Gaussian observers. So these are basically inspired by that result that you saw before. These are basically basis functions or channels in the frequency domain that peak at different frequencies. That these are like a band pass filter. So they, like in the previous case, they don't see the zero frequency. They see some middle frequency fairly well, and then they don't see very high frequencies. Large objects are hard to see. Small objects are hard to see. And what we do is we combine several of these channels to create a filter that we're going to say acts like a human visual system. So using that model, what we end up getting is, so now we have here experimental data from 4 observers. The solid line is the average performance of the 4 observers. And then the star, the blue star, is this model that uses these 3 channels and a template that we showed earlier to predict the performance of the average human. And what you see here is that it follows pretty well. You see that the model overestimates performance at large amounts of regularization, but for a simple model and real data, this is a pretty nice result. So it's pretty exciting to see that not only can we evaluate images using these kinds of studies, we can also predict the performance using mathematical models, because the experiments take a long time. So if you have a mathematical model that's predictive, it saves you a lot of time. Now, so what we see is that the root mean square error and SSIM overestimate the effect of regularization on human observer performance, and we have a reasonable way of modeling human observer performance using the SNOT, the channelized model observer. For the third aim, we're going to start looking at deep learning. So this is something that is very of high interest right now, because neural networks are not as well understood as previous methods of generating images. So we want to use this detection method, detection-based evaluation and model observers to study neural network reconstructions. So the first question to ask is how much to undersample with a neural network. So if you undersample a lot, basically, if you collect half of the data, you can go twice as fast. If you can collect a third of the data, you go 3 times as fast. The less data you collect, the faster you can go. And if you've been in an MRI scanner, you'd rather go as fast as possible. But you don't want to decrease the quality of the images. So in the artifacts for neural networks are harder to predict than the artifacts for constrained reconstruction. And what we see here is the original image, and then a neural network reconstruction with different levels of acceleration. And what we see is that as you keep accelerating, you start seeing these structures that were not in the original image. So these are called hallucination artifacts, because a neural network learns the structures and uses to fill up an image, but if it doesn't have enough data, it starts to put things in there that are not really there. And that's a really dangerous thing to do in medical imaging, because some of these structures that the neural network is putting in might look like a tumor. So the whole idea is, like, how far can you accelerate without introducing these, or are there different types of neural networks that is going to decrease, this issue? So now let's look at what happens if you have a lesion in there. So now you have the original image with a signal, and then we keep accelerating, and you can see here how it becomes fainter with 2x, a little bit more faint with 3x. Doesn't seem to be there with 4x. Then it seems to jump out with 5x, but then there's all this other structure around it, right? So this is highlighting an area of research of trying to better understand how we can quantify this. Again, pause the video for a second. Given what you've seen, how far would you accelerate? Now, so that's the question that we're going to do, but try to answer, but with the kinds of observer studies that we've seen before. So this is explaining what the undersampling is, and this is an undersampling for a 3x acceleration. And we can see that in this undersampling, it's not random as in the previous case, it's uniform undersampling, and we're going to use a unit, which is a type of neural network to the reconstruction. Now, what we found, and here we're evaluating using both the structural similarity, the root mean square error, the Laguerre-Gauss channels, which approximate the ideal performance, and the human experiments. So this is not an SDoc, this is actual human experiments. And this is the full reconstruction. This is not undersampled. And then this is different levels of undersampling. What I want to say is that the biggest jump that occurs between one level of acceleration and another occurs between 3 and 4x for SSIM, root mean square error, and Laguerre-Gauss. For the human, it occurs between 2x and 3x, which basically means that the first place where there is a large drop of undersampling occurs earlier from human observers than for machine observers or standard regularization methods. the reason why it's interesting is that most people use SSIM and root mean square error for evaluating their algorithms. So this would suggest that they would expect a larger amount of acceleration possible. But when you do an observer study, it seems that it would be a smaller amount of acceleration that you could do. So this is indicating that maybe we're overestimating the amount of acceleration that we can do. And that's the basic punchline of that work. And we are expanding this work by looking at different loss functions, modeling of the human observer. And we used a unit in this case, but using a neural network where we incorporate not only the learning part, but also the physics of it. So this is a feature work, which is going to be more aligned with what is currently being used in clinical studies. So another question that you could ask is which architecture you should use for your neural network. So this is a unit, and in this setting, we train with 500 images. It's a very small number of images as far as neural networks go, and we constructed on 50 testing images. In medical imaging applications, there aren't as many training sets as in other applications. We later have seen larger training sets and have similar results. But you can see this is a unit. Basically, it starts with an image representation, goes down to a feature space, and then it comes back into an image, and it has connections that allow you to skip, the unit itself if it turns out to be better. So what do we have here? We have a sample reconstruction with a 3.48 undersampling factor with 64 initial channels and 0.1 dropout. So you can, in the network architecture that we're considering, you can pick the number of channels that you start with. You can also pick the amount of dropout. Dropout is a way to regularize your neural network. It basically says how many of the connections are you updating in each pass. And what we have here is the original image. And this is the undersampled image, which is the input to the neural network, and the reconstructed image. So we see that the neural network is learning how to undo some of this aliasing in the image going from the undersampled image to the reconstructed image for this particular network architecture. Now, something else that we want to identify is that we also have hallucination artifacts in this case that are hard to assess. So what we have here is a signal. The signal is in the center of the image, but in this particular choice of network reconstruction, this is for 64 channels and 0.3 dropout. It's a much larger amount of dropout. There are these hallucination artifacts that are not where the signal is. So if you're doing the kind of task that we're doing, basically saying, is the signal in this location or in that location, you would still be able to see that tumor there, even though there were these artifacts that came up which are not physically realistic. So this is identifying a limitation with our approach. Our approach doesn't capture these other artifacts that are appearing in your image that are important clinically. So what we explored were different combinations of number of channels and amounts of dropout. And what we have here is the human observer studies, SSIM, and root mean square error. And if you look at which one did best, they're the same basically in terms of with sanity with uncertainty, the 0.3 dropout and the 0.1 dropout in terms of human performance. But as we saw before, the 0.3 dropout had those hallucination artifacts, and the 0.1 dropout did not. So the root mean square error and SSIM capture the hallucination artifact. So they're actually choosing the 0.1. So even though in my research I tend to push detection-based methods, not the root mean square error, this is a setting where the combination of two sort of led to a better result than just using a two alternative force choice study. Now, this highlights the unintuitive nature of choosing hyperparameters and their effects. Signal known exactly tasks may not be the best for optimizing clinical use. You might want to do them in comparison to mean square error. And really, the best task performance might not imply the best artifact reduction. So we have to consider both of those things, when we're doing evaluation of image quality. And future work in this case would be looking at implementing a search task, which we hope would be more realistic and help to account for some of those hallucination artifacts. So I just want to thank you again for your time. I look forward to the Café con Leche where we can discuss this research. And thanks again to the organizers for inviting me to give this talk.